So the recording is on. So today will be the last class of this particular course. We'll finish microwave filters, which we started in the last class. So these references we have gone through. Collier and Podzar were used mostly throughout the course, and Cheng and some specific points like Smith chart and other topics. So we're finishing module 9 today. So this entire course was outlined for passive devices. Maybe in future I'll offer an course on active devices as well. The last class we started with microwave filters and covered periodic structures and started with the image parameter method. So we'll finish image parameter method and then look into insertion loss method and then filter transforms. So we'll start with a quick recap of the image parameter method because we'll continue with that. So we just in the last class we just found out the image impedances and then the propagation constant, and now we'll look how to design filter from them. So this was the initial circuit that we had, and Zi1 and Zi2 were the image impedances as port 1 and port 2. So the idea was we are terminating the this two-port network with image impedances, and then we are trying to find out the propagation constant for this in, inside this two-port network. So we did all this mathematics, found out the image impedances in terms of the this ABCD parameters, and then terminated the circuit with the image impedances. And then we use the this ABCD parameters and use the voltages, and we did it for both the ports. And we looked at if it is symmetric, and in that case we'll have I Zi1 equal to Zi2. So this was all straightforward. This involved a lot of mathematics, and so you can go through these steps, write down them by your hand, and then it will become more clear if there are any doubts. So then we use this information, and then we try to write down the voltage ratio and the current ratio. And in the over there, we found that this root over d by a, this particular term, was inverse in the current ratio, and this particular term was constant. So we declared this term to be the propagation constant for like e power minus gamma, and so this is related to the propagation constant, and this root over d by a term as the transformer turns ratio. Now once we had this, we can like with this relationship over here, e power minus gamma equals to root over ad minus root over bc. we uh, we we have our propagation constant as this complex this gamma as alpha plus j beta, and using this particular information we can find out this gamma and cos hyperbolic of gamma. So we found out cos hyperbolic of gamma is root over AD, and we covered this till here in the last class. And then we wrote down the ABCD parameters, Z parameters, and image impedances for the T network and Pi network. And this table I borrowed it from Podzar, so it is there as well. So once we have this particular table with us, we can use it to design filters. So we start here today. So we will now once we have found out the image impedances, we can start designing the constant K filter. Now the first structure design that we'll be looking at will be a low pass structure for a T network. So for this particular circuit, we got it from the table which we saw just now. And over here, if we replace Z1 by L and Z2 by C, we achieve this particular circuit. And intuitively, if you see, the series inductor and the shunt capacitor, they tend to block high frequency signals. So like during my undergrad, one of my professors told me that if you have an AC signal coming over here and it can go through the capacitor exam. So this is something which is taught in coaching, I believe, as well. So if you have an AC signal, it can pass through it, but if it is a DC signal, it will get blocked. So if you find it confusing, sometimes don't I get confused, so I just see where the capacitor is and believe that AC will pass through it. So for high frequency signals, uh, this will uh, this will get blocked because it will go to the ground, and the low frequency signals, for example, the DC will pass through it. So okay, so we're looking at low pass and T network. So continuing with our discussion, from this particular table, we have the uh, expression for the image impedance for T network, and which is given by root over Z1 Z2 multiplied by root over 1 plus Z1 by 4 Z2. So we from the table we have this expression, and once we substitute the value of Z1 and Z2 over here, we get the image impedance expression for this T network over here, this low pass T network. So once we have got this, so this is the image impedance, and then using this, if we just take the look at this term and equate it to zero, we can define a cutoff frequency where this particular term becomes zero. So which turns out to be root over uh, uh, 2 by root over LC. Okay, so these things we saw in the last slide, that we are giving defining Z1 and Z2 as G omega L and 1 by G omega C, and we have got the cutoff frequency as this over here. Now we can also define a nominal characteristic impedance, root over L by C, and this is constant, and hence we call this as constant K filter. So this K over here is equals to the R naught term that we saw in the previous discussion. Okay, so we have the image impedance over here for the T network. We have the cutoff frequency. We have the nominal characteristic impedance, and we can now use this value, substitute it over here, and uh, use the expression for cutoff frequency as well. And this is the final expression for our nominal characteristic. The image impedance for this T network. So we now have the image impedance in terms of R naught and omega C. And if we look that for omega equals to zero, that is when this becomes zero, the image impedance becomes equal to the nominal characteristics impedance. Now from this particular table over here, we can we can find out the propagation constant as well. So all we need to do is substitute the value of Z1 and Z2, and if we do that, and then we replace this L by C and K. Yeah. So if we once we substitute this root over omega C and uh, R naught everything into this expression over here, then we will end up with our propagation factor looking like this. So this is our propagation factor. And once we have this expression over here, we can find out the relation we can plot the propagation factor with respect to this omega over here. So now we'll do that. So since we defined our cutoff frequency, let me just put all these things over here. So once we have we got the propagation factor, we can write down its magnitude by this expression over here, and we had defined a cutoff frequency, right? So omega less than omega c and omega greater than omega c. For these two regions, we can plot the magnitude of this particular function. So for less than omega c, it turns out that ZIT becomes real, and gamma is imaginary. So since gamma is imaginary, we will see propagation, and we can plot beta over here. So gamma is equals to alpha plus j beta, right? So if this particular term is imaginary, alpha becomes zero, and we have just beta over here. And if we try to plot that, plot this against the frequency, we see beta like this. This is the plot for beta, and for omega greater than omega c, this the zit becomes imaginary, and e power gamma becomes real. So when this becomes real, it implies that now we have non-zero alpha, and this propagation factor becomes zero. This becomes zero, and we can plot the alpha value. Okay, so this is the alpha value. So we have attenuation over here, and we have a propagation over here. So this particular two-port network that we defined, for which we found out the propagation factor, shows that below a certain frequency we have a pass band. We have, that is, we have propagation, and above that particular frequency we have high attenuation, that is a stop band. So and you can see this nature that at lower frequencies we have pass band, so and higher frequencies we have stop band. So this acts like a low pass filter. So I'll just pause over here and let you read at the expressions and the text. So if you have any doubts, you can ask them. Otherwise, we'll continue with our discussion.
Hello, I'm audible.
Yes,
Yeah, you can continue. I will go through
yes,
later.
Caliban, you were. Yeah, I can't hear you now. Um,
Yeah, you can continue. I will go through later actually.
Yeah, sure. Okay. Yeah, great. So if you have any doubts, you can also type them in the chat.
Yeah,
I'm just giving some space for you to read and go through the text, just in case if you have any doubts. Okay, I'll continue with the discussion. We also have a lot of material to cover today. Okay. So we started with this circuit over here, and now we have um, got the plot for at alpha and beta against frequency, and we saw the pass band and the stop band. Now, if you observe, the attenuation alpha is zero at the cutoff frequency, and relatively small uh, near this. So this attenuation is very less near as soon as we start the stop, like near the stop band. Like when so this pass band we don't have any attenuation, and this particular plot starts really slowly. For an ideal filter, what the required will be like. So this is our pass band, and the attenuation should start rapidly, and it should saturate. So there should be no propagation over here, and no propagation over here, and propagation over here. So so there is this issue that this attenuation is very low near the cutoff frequency, and we expect it to be something like this. So if this it was like this, then it would attenuate all the frequencies near the stop band, beginning of the stop band as well. And so also, since we defined a constant k, we call this as a constant k low pass prototype, and this is a low pass filter. And there and over here that for the circuit, if you see, we only have two parameters, is L and C. These are the only two things that we need to specify to design this particular filter. But whatever discussion was covered over here can be extended to like cascade this and form a higher order filter. So that can be done. And one thing that is important is that these results are only valid for when filter sections are matched, that is terminated in its image impedance on both parts. So we had this two-port network, right? So we need to make sure that they are terminated by their image impedances and on both the sides. So how would you then match it with the other parts of the circuits? So when we implement these circuits, what we do is if we are working with the microwave frequencies, we are usually using distributed elements, for example, this L and C, and model them using microstrip or strip lines. So so what will happen is we whatever L and C value we want, we might have some uh, patch over here like this, and then patch over here like this, and then okay. So this is something how this is something how it will look like. So it might happen that this particular the thickness of the transmission line over here will should be of the image impedance value. Image impedance is over here. And then if you want to match it to the other part of the circuit, for example, over here, and if that has a 50 ohm over here, then 50 ohm over here, then you can, in between this, you can use a quarter wave transformer. Quarter wave transformer over here, and then a quarter wave transformer over here, and then match it to the 50 ohm. This these transformers you will need, and then again these transformers are also frequency selective. So there will be this issue over here. So if you're working at a very narrow band uh, frequency, then this works fine. Otherwise, you'll have to look into broadband matching techniques so that you can match it to, with the image impedances. So there are some issues with this particular technique, and hence we prefer to use the insertion loss method. And also to avoid this image impedance thing and get better attenuation, what we do is we use what we call an M-derived section. So we'll see that in coming slides how we design an M-derived section. Over there, we modify this particular circuit to include two elements over here and get a better attenuation in the stop band. So we discussed the T network. Now we discussed the T network, and now we'll look at the pi network. So taking like I snipped this out from the table which we saw earlier, and over here we had this pi network, and now we are replacing Z1 by inductor and Z2 by capacitor, and so we end up with some circuit looking like this. And for this particular circuit, we have the ABCD parameters, the impedance parameters, the image impedance, and the propagation constant with us. Now we'll use this and to rewrite the propagation factor. So whatever we did earlier for the T network, we can do the same. And now once we have the Z1 and Z2, we just substitute this over here, and again we have the same we get the same expression for the cutoff frequency and the normalized nominal characteristic impedance. So we use them and we write this propagation factor. And we by using this propagation factor, we again plot the attenuation constant and propagation constant, and we achieve the same graph over here. So since the this particular propagation factor looks the same, we have the same expression, we'll get the same plot. And all the discussions that we did on the previous slides will hold true for this case as well. So we can design the low pass filter using T network or pi network, T or pi network. So by either using both the cases, we can design this low pass filter. And one interesting fact is that at omega equal to 0 at over here, we what we see is that the image impedance for the T network and the image impedance for pi network, both of them become equal to R naught. So just in case if this comes as a Viva question or your asked, this is an interesting phenomenon that you could notice. But otherwise, generally they are not equal. So we discussed low pass T network and low pass pi network. Now we can use whatever discussion that we did in the earlier slides to form a high pass constant K section. Does that instead of where we had L, we now have a C, that is we are placing inductors and interchanging inductors and capacitors. So again we have the T section and the pi section. And if you notice, we had inductor over here and capacitor over here for low pass, and now we are interchanging them to get a high pass. Now, if you try to solve them, I'll leave this up to you. You'll end up with the design equations looking like this. So we have R naught, which is same, and omega C instead of 2 over here, we this 2 comes down. You can try to solve them. This will be fairly straightforward. And I will leave this as an exercise to derive the expression for the propagation constant. So you can use that table that we saw earlier, and over there you have the expression for the propagation factor. Just substitute in the values for this Z1 and Z2 in terms of j omega L and j 1 by j omega C. Just substitute them in that expression from the table, and then you can write down the expression for propagation factor, and then see when this propagation factor is real or imaginary, and then you can plot the alpha and beta against normalized frequency. So I leave this up to you. You should see the um, uh, pass band in the high frequency, and so you'll get a pass band over here and the stop band over here. So I'll leave this as an exercise. That's all for the constant K type of filters. And now we look at the M derived filter section. So the constant K filters had their at the near the stop band, their attenuation started very slowly. But we expect this attenuation to be very rapidly. So it should start very rapidly, and we should have attenuation in the entire band. So for this, we use an M-derived filter section, and for the derivation of the M-derived filter section is very fairly straightforward. What we do is we replace this Z1 and Z2 with Z1 dash and Z2 dash, and then we try to evaluate. So we and this Z1 dash and Z2 dash, they we so we for this Z1 dash, we write it in terms of MZ1. So and then we are trying to then we'll try to find out Z2. So once we have this Z1 dash as MZ1, we find out the image impedance. So this is the expression for our image impedance, and then we can when we try to solve it for Z2, and this we end up with this expression over here. So this Z2 dash has two terms, this Z2 and Z1 with some coefficients in terms of this M value. So if you we can represent this Z2 dash as a combination of two elements. So, and when we try to substitute the value for Z1 dash and Z2 dash, so Z1 dash becomes MZ1 by 2 and MZ1 by 2 over here. And Z2 dash becomes this first term Z2 by M, and the second term 1 minus M square by 4M Z. So try evaluating this expression over here, and you will end up with this uh, term which has two of these values, and we can just use them to modify the this Z2 part. So the Z2 we modified it to Z2 dash, and now this Z2 dash is equal to this term. And look closely that this Z1 and Z2, we have not decided whether it is inductor or capacitor. They could be either. So and for M equal to 1, this reduces to the original constant K section. So if you put M equal to 1, this thing will go away, and this will become Z1 by 2 and Z1 by 2 over here. So we discussed how we modified. Uh, we got this particular circuit from the constant K, from constant K to this particular circuit, and now we had the expression for Z1 dash and Z2 dash. And for a low pass filter, we have seen that we have inductors over here and capacitors over here. So if you recall, we had inductor and this capacitor over here. So we had Z1 equals to L and Z2 equals to C. So now we'll just substitute this L and C. Okay, j omega L. So the frequency term 1 by j omega C. So when we substitute them, we get j omega Lm for Z1 dash and 1 by j omega Cm plus 1 minus M square by 4M j omega L for Z2 dash. So these we now have the expressions for Z1 dash and Z2 dash. So clearly this is an inductor, and Z2 dash has a capacitor and an inductor. So once we use these values and substitute them over here, this is what our circuit will look like. So we'll have inductors over here and a capacitor over here. So this is the M derived filter section, M derived low pass, and for T network. So taking so if you start with a pi network, you will end up with a and then if you substitute the value of Z1 and Z2 according to the low pass, then you will end up with M low pass pi network. So all these solutions are fairly simple. It involves a lot of mathematics and making sure you don't mess up with the signs or something. You'll end up with the correct answer. So now the propagation factor for the M derived section again. So this again looks is a T network, and if we use the if we and we have we can write the impedance value for this side is equal to Z. So this is your Z1. If you simply rewrite it as simply Z, this is Z1 and this is Z2. And now using again the table, we can write down the propagation factor. And once we have the propagation factor, okay, Z2 dashes, right? Yeah, sorry. So Z1 and Z2 dashes over here, and then we substitute the values inside this. So once we do that, so let's first try to evaluate Z1 by Z2 dash. So this, since it is present over here, and present over here. So if we evaluate Z1 dash by Z2 dash, we have this expression over here where this omega c is 2 by root LC. And then we can write 1 plus Z1 dash by 4 Z2 dash equals to this expression over here. Okay, so we found out Z1 dash and Z2 dash, and then the propagation factor and the cutoff frequency. And we have this expression over here for 1 plus uh, Z1 dash by 4 Z2 dash. So if we restrict the value of M from 0 to 1, then we see that this e power gamma, which is the propagation factor, it is real, and this its magnitude is greater than 1 for omega greater than omega c. So since it is real, we have alpha non-zero and beta equals to 0, and hence this is the stop. Hence we have the stop band beginning from omega c. So for higher frequencies, since if this is our plot over here and omega c is over here, for values of omega greater than omega c, we have a stop band over here. So so again the stop band begins at the same place where we had it for the constant k. But, however, for a particular value omega equal to omega infinity, we have this particular expression over here. So if you try to see this denominator over here and equate to 0, we have a frequency omega infinity. We can label a frequency equal to omega infinity, where this particular term becomes 0, and and at that frequency, this particular this whole thing becomes infinite. So we have an omega infinity over here as well. So if we try plotting this propagation constant now, so we have omega c over here, and then the attenuation rises very steeply, and then at omega infinity the attenuation becomes infinite, and then the attenuation reduces slowly. If you try to plot this, so this allows a very sharp attenuation at near the cutoff frequency. And if you remember, our constant k filter gave us the plot for attenuation like this. So this is the attenuation due to constant k. This is the attenuation due to M derived. And if you take a composite look, so if you try to cascade this particular thing with your constant K filter again like this, so you will end up with a composite response like this. So I won't go deep into this composite response. I would recommend you to go through Poser. It is usually not covered inside the UG syllabus. I'm not sure about masters. We did not cover it, but yeah, this is important if you are looking into uh, filter design by the image parameter method. Usually we go for the insertion loss method. So, but knowledge of this will be good. So we won't cover it today, but just to give you an idea, we this is the attenuation due to an M derived section looks something like this, and the constant K gives attenuation like this. And if you take a composite look, then you can end up with a filter which has attenuation looking something like this. So this is very good. This is excellent if you are able to do it for a wide band of frequencies. So I believe this is all that we need to know for filter design by the image parameter method for a low pass filter. For a low pass filter, and all these things will hold true if you just modify this for a pi network or just interchange this L to C or C to L. This will turn into a high pass filter. So now we'll begin with the insertion loss method. Maybe if you have any questions, you can ask them now or type in the chat. So we'll start with the insertion loss method. Just in case if you have any questions, you can come back to me. Since we have a lot to cover, we'll do it quickly and wrap up this course.
Yeah, yeah, sure.
Okay. So we as we saw in our discussions now that insertion loss that the image parameter method had its own disadvantages some places, and it becomes complex if you are trying to design a filter of higher orders. And usually what we are looking at, one of the major problems was the image parameter method requires the circuit to be terminated by the image impedances, but uh, which becomes very difficult if you're designing multiple filters, and if you want it to like, it does not allow us the flexibility. So the preferred method is the insertion loss method, which allows a higher degree of control over the pass band and stop band. And also we'll see how like filter this insertion loss method gives us more flexibility based on what kind of filtering that we want to do, like what is important and what kind of circuit that we need. So, for example, if you're looking at the if you're looking at the phase characteristics, or if you prefer amplitude, so in that cases the insertion loss method gives us different ways to tackle them. So so you might like, for example, if you're working on a certain filter and you are more focused on that the particular filter should have very good pass band and stop band characteristics, and this amplitude of the signal that you're receiving should be very good in the pass band and should be very low in the stop band. So if this is your concern, then you can go for a Chebyshev filter, which has a very sharp cutoff over here. And if you want that the amplitude should be like not disturbed. For example, what happens is in the Chebyshev filters we have ripples over here, and if you prefer that it should be very smooth, the passband should be very smooth, then you can go for a binomial or a the binomial filter, which gives the minimum insertion loss. So for example, if you have a low pass filter, it will be this maximally flat, we also call it. So it will be very flat over here, very close to the like whatever signal that you're transferring, it will go through. But what happens is you will this roll off will be very slow, and passband and the stop band, uh, it there is no as such very sharp cutoff over here. And then it might also happen that you want better phase response, and in that case you can use a linear phase filter design. We won't cover this, but this is there in Podzar, and you can refer to other literature as well. So we'll look into the binomial this maximally flat filter design, and we'll for Chebyshev also we'll discuss. We'll go to a little depth for mathematics of this particular thing though, and we'll use the inferences got from here to design Chebyshev filter. Or also, so whatever discussions that we'll do, so we'll discuss a filter of order 2. I'm just telling this earlier only. So we will discuss, we'll do design a second order filter, and and whatever discussions that we are done that we'll do can be easily used to design even higher order filters. So we'll see this. We no need to rush this now. Let's first look at a very simple filter design. And yeah, so when I said order, this order means the number of reactive elements. So if you have an inductor and a capacitor, so this is a second order filter. And if you have one more inductor, this becomes third order. If you have one more capacitor, this becomes fourth order. So this is what the order of a filter means. That is the number of reactive elements. So let's first look at what when we are saying this insertion loss method. So what is this insertion loss, and like how are we going about it? So the first thing that we need to do is characterize the power loss ratio. So we're designing a filter, and for example, this is our filter. So we are sending some power over here, power input, and we get some power output. So depending upon how much power we want out in the output, how much are we okay with, we can define a ratio called the power loss. So the power loss ratio is the power available from the source and power delivered to the load. So this is the incident power by divided by the power like which was delivered to the load, and this is the like using the reflection coefficient over here, how much power was reflected back. If you subtract it through this circuit, we get this power loss ratio. And if you look closely, this is basically the S21. So this particular denominator is this is the S21, and this entire thing is the reciprocal of the sorry, S12. S12. Okay, so it is saying both. Yeah. So if both load and sources are matched, then this is S21. Yeah, this is S12. Sorry. Okay, so we have defined the power loss ratio, and this is very important if you are to design what like for your designing of your filter. And now we can define the insertion loss as 10 log PLR. This PLR from here, and this is your insertion loss. And this is a gamma omega square. This mod is an even function of omega. So I'll leave this for you to verify. So this is somewhere present in chapter 4 of Podzar for your reference. Check and derive it. See how it is an even function of omega. And hence it can be so if you assume this now, that if it is an even function of omega, we can write this gamma square in terms of a polynomial of omega square. So this is this if you assume this is to be true, so we have m omega square and m and n. So m and n are both real polynomials in omega square. So we are defining this ratio expression over here. And then we can use this to write the power loss ratio in terms of M and N. Now, for a filter to be physically realizable, the power loss ratio must be of this particular form. So this form will come again and again, and this is important. And depending upon how this form, especially this particular ratio over here, changes, we can define different kinds of filters. So we'll discuss some practical filters now. So just in the previous uh, slide, we derived this expression for the for a filter, and for a maximally flat or binomial or a Butterworth uh, filter, that is, we want a very flat. For example, if this is our we're designing a low pass filter, right? So let's stick to low pass filter. And if we want a low pass filter, the power received the power received, and we want this to be maximally flat, so we want this to be very flat over here. So for if we want to stick to this particular power loss uh, ratio will have to look something like this. So this is the expression for a Butterworth filter. So you'll have to remember this for now, because this involves more mathematics. But yeah, so if you remember this, this is the expression for a Butterworth filter. And now, if you have this, then you have to we have this n over here, which is the order of the filter, and we have this omega c over here, which is the cutoff frequency, and k gives you the amount of the insertion. K gives you the amount of insertion loss at the cutoff frequency. So if you plot this PLR with this omega, it will look something like this. So I'll just highlight this part. If you can see where this red line is, so this is the maximally flat response, and when if we plot this expression over here, so we this at the cutoff frequency, if you substitute this omega equal to omega c, this particular thing becomes 1, and the power loss ratio at the cutoff frequency is 1 plus k square. So based on how much power loss how much the fraction of power we want at the cutoff frequency, we can determine the value of k over here, and based on the order of our filter that we want, we can determine n, and we must know the cutoff frequency for the filter design. So based on the insertion loss at the cutoff frequency, the knowledge of the cutoff frequency and the order of the filter, we can completely determine this particular expression over here. And if you see for omega greater than omega c, the attenuation increases monotonically over here. And this is if you try solving it, you will achieve that this is 20 n dB per decade. So this is how this is the order in which this the power loss increases. Okay, so now similarly, if we want for the same order, if we want a sharper this cutoff, so this is the equiripple response. What will happen is inside the pass band, we have this ripples over here. So hence we call this as equiripple. And to get this response, we use a Chebyshev polynomial, and a Chebyshev polynomial for nth order filter, where the expression is given by this over here. So we have this function Tn square omega by omega c, and this allows a sharper cutoff, but and this particular Tn oscillates between plus and minus 1 for x square less than 1. So hence we have these oscillations over here due to this Tn function. And this for omega equal to omega c, this particular the insertion loss again becomes equals to 1 plus k square, and determining how much insertion loss we are able to afford. And Yeah. So the power loss for the omega greater than much greater than omega c, we have this expression over here, and again this increases at the rate of 20 ndb per decade. So if you compare the Chebyshev case, the insertion loss is 2 power 2n by 4 greater than the binomial response for for higher frequencies. So this is how we compare the equiripple and the maximally flat responses. So depending upon how much, if you want a sharper cutoff at for a lower order, you can use this equiripple uh, filter, or if you want a maximally flat response over here, then you can use this Butterworth filter. Now, the other kind of filter which is popular is the elliptic function, and the elliptic function has ripples in the pass band and the stop band both, and it has a very sharp cutoff. But the design of the elliptic function low pass filter, this elliptic filters are usually complex, and we won't go into it. But if you are working on filters and you want to read this in detail, you can refer to microwave transmission line filters by Mahler. Uh, yeah, so for this, so what all you need to do, you have to specify Amax and Amin and some other function, some other properties. So, and then you can do this, but this is complex and out of scope for this particular course. But you should know that we have elliptic function as well. Now, we saw the Butterworth filter, the Chebyshev filter, the elliptic filters, and we have something called the linear phase response. So, based upon what kind of function, like output we want, we can specify, we can use that particular kind of filter. So for our discussions, coming discussions, we'll focus on low pass filter prototypes. And once we have this low pass filter prototypes, we can use them to achieve low pass we have already designed. And then we can get the high pass band pass or band stop filters. So this particular prototype will actually be in terms of normalized terms. So it will it will the impedances and the frequencies, they will be all normalized. And once you have this particular prototype, you can just scale them to whatever impedance and whatever frequency you want, and you will have the filter ready. So this is the design flow. First, we find out the filter specifications. For example, how much insertion loss we want, what is the order of the filter, what is the cutoff frequency, and then we do a low pass prototype design. Then we do a scaling and conversion, and then implementation. So for implementation, we won't cover this. You can refer to Ozar. It will have something topics on Richards and Kuroda's, Richard transforms and Kuroda identities. Richard transforms and Kuroda identities, you can use them. And the implementation is fairly straightforward if you already have designed your filter. So we'll cover it till here. I'll just give you a brief idea of how implementation is done. So let's look at maximally flat low pass filter of second order. Since we have two elements, this is a second order filter. And uh, so the source impedance, we have normalized it, and hence it is 1. And whatever the values that for L and C will get, they will all be normalized. So this we're considering this two element low pass filter, and we have L and C, and we're looking for a maximally flat response. So the source impedance is 1 ohm. The cutoff frequency, since everything is normalized, this will be omega c equals 1. And the desired for this particular n equal to 2, and since we are looking at a maximally flat response, the desired power loss ratio should look something like this: 1 plus omega power 4. So if you remember, this was 1 plus k something 2 power omega by omega c whole power 2n, something like this, right? So this turns out to be 1 plus omega power 4. And now we try to find out the input impedance looking from over here, and you can try solving this, and this is what we will achieve: 1 plus j omega l, and this parallel terms over here. And we can define the reflection coefficient over here, gamma, as zn minus 1 by zn plus 1, since this we have everything is normalized. And once we have defined this gamma, we can define the power loss ratio as 1 minus gamma square, substitute the value of gamma over here, and then substitute the value of zn at all these places from here. So this is some this particular expression will evaluate to this expression over here, and now we'll try to find out what this expression is. So we found out Zn equals to this expression, and now Zn plus Zn conjugate is 2r by 1 plus omega square r square c square, and 1 Zn plus 1 square is equals to this huge term over here. So this is all multiplication with numerators and denominators. We're substituting the value of this Zn over here, and then finding out Zn plus Zn conjugate and Zn plus 1 square. Now, once we have found out these two terms, we substitute them into the power loss ratio term. This term over here and this particular term over here. We're just trying to find out power loss ratio for this particular circuit. And so after a lot of this simplification, this is what we end up with. The power loss ratio is this expression. And now we have to compare it with the ideal what we wanted for a maximally flat low pass filter. This should look like this. So on comparing these two expressions, we find that r should be equal to 1. If this r becomes equal to 1, this term becomes 0, uh, and this particular coefficient should also be equal to 1, and this particular coefficient should evaluate to 0. Okay, so to make this term vanish, we found out that r equal to 1. Now we'll equate this particular term equal to 0. Okay, so coefficient of omega square must vanish, so we're making this 0, and once upon making this 0, we find that L should be equal to C. And again, since this term is also should be equal to 1, and we have r equals to 1 over here and L equal to C, we can find out the value of this L and C both are equal to be root 2. So now we have found out the value of L, C, R, everything. And whatever discussion that we did now can be easily extended to not easily, can be extended to any number of any order of filter. But since this will become more complex with increasing orders, so this sometimes becomes very difficult for higher order filters. But need not worry. There have been scientists and researchers who have done a lot of work for us. So just in case, if we, for example, if we extended our design, we had this circuit, right? We had a resistor, we had an inductor, and we had a capacitor like this for a second order filter. So if it was increased to a third order filter or a fourth order filter, so this it will look something like this. And we could also have its dual like this, where we had a current source and it started with the shunt impedance, and then we had the first element we had was an inductor, and the second element was a capacitor. While the first circuit that we discussed had the first element as the capacitor and then an inductor. For either of these cases, we have a table where we have all the normalized value found out for us. So just to like make it clear, both these circuits will have this, since they are dual of each other, they will have the same filter response. And the only thing needed to find out the values of the normalized values are the insertion loss uh, at the cutoff frequency. Now take a look at this table. Once we have defined, for example, if we are just trying to design a filter, and we should know the order of the filter, for example, 2 or whatever, the order of the filter, the cutoff frequency, and the insertion loss. So based on the insertion loss or knowledge, we decide which kind of filter we are trying to use. So example, if we are choosing maximally flat, so we'll refer to this table, which is there in Podzar. Okay, so I'm missing the table number. So you can find this in the chapter where they have discussed microwave filters. So once you have chosen maximally flat low, low pass filter prototype and the order of the filter, for example, if you choose 4, then you get the value of G1, G2, G3, and G4, uh, and G5 as well. So G5 will be the last impedance value, right? So if you to the previous slide, this is your G5 fourth order filter. This is your G5. So so you have a resistor over here, which is 1, and then you have a capacitor, and then an inductor, the capacitor, and inductor. So this is your fourth order filter, and then you have this load impedance over here. So this will be your G1, this is G2, this is G3, this is G4, and this is G5. And the normalized values, you can borrow it from this table over here, and you can do it similarly for the other order filters as well. So up till 10, this has been this is available with us. And so once we have chosen the order of the filter, we get the normalized values. And this is the plot for the frequency response, that is the attenuation with the frequency. So you can see for a low order filter, the attenuation is pretty low. And if we increase the order of the filter, it becomes really high. But one thing that I have missed to stress is that if you increase the order of the filter, its complexity increases, and it is more difficult to like include on the PCB that you're working on. So increasing the as much as like if we want a better frequency response, we can always go to a higher order filter, but we need to keep the circuit simple as well. Now looking at the equiripple low pass filter prototype. So again, this we have the same circuits over here, and for the this equiripple thing, we will use the Chebyshev polynomials. So this expression we saw in the previous discussion. The power loss ratio is given by this expression, where we have this Tn function over here. And this Tn is 0 for odd values of n and 1 for even values of n. So for odd values, the insertion loss is 1, and for even values, the insertion loss will become 1 plus k square. And this 1 plus k square is also the ripple level in the pass band. So this is if we have chosen to design a equiripple filter, and then we have chosen the order of the filter, and then again we have the same circuits. It's just that the normalized values will change. So this is the table for given for the Chebyshev or the equiripple filter. So once depending upon the insertion loss that we are looking at, or if you're chosen to use equiripple filter, and then we choose the order of the filter, then for example, if we now again we are looking at a fourth order filter, then we have G1 to G5 over here, and the same circuit, the resistor, a capacitor over here, and then inductor over here, the capacitor over here, inductor over here, and then our load value over here. So again, we will have this as this is the G0, G1, G2, G3, G4, and G5. So we get their values, normalized values. And so this particular table is for 0.5 dB ripple, and this particular table is for 3 dB ripple. So this 3 dB and 0.5 dB refer to as if we have small ripples over here and this passband, and or if we have large ripples over here. So depending upon that values. So this is over here we have the 0.5 dB ripple, the attenuation. So attenuation becomes again this very slow for uh, low ripple and low order, and very fast for higher order. And you can see we have a higher more attenuation to begin with in a 3 dB ripple, and this is the higher attenuation for a 3 dB ripple, but this is for lower order, this is less, and for even higher order this is high. Now whatever design we did till now was uh, we were using cutoff frequency as 1. So now if we now and yeah, and all the values that we got for this G1, G2, and GK, they were all for normalized values. Now, once we have designed the low pass prototype, we need to do what we need to do is we have to scale it to the correct cutoff frequency, and upon scaling them and normalize it to the correct characteristics impedance that we're looking at. So, so now we need to scale this. For this, we'll use this filter transformations. So, so our discussion started with RS equal to 1 and this cutoff frequency equal to 1. So we start with impedance scaling. So, if we let the primes denote the scaled quantities, that is earlier the whatever the normalized values that we got where are the non-prime one, this L and C, the value of G naught, G1, G2, they are if you have chosen, and they will correspond to some L and C values, right? Not G naught, sorry. G naught will correspond to R. So G naught will correspond to R, and G1, G2, they will correspond to C and L. So using this, you can find out, you can scale the values. So once, so RS was the normalized value. R naught is your correct normalization value. For example, if you are looking at a now you found out to this for 1, and then you have your inductor and then a capacitor. Okay, and now you want to scale this 1 to 50 ohms. So this R naught will become 50 ohms, and whatever G value you got it from the table, you will multiply that and you will get your inductor value. Similarly, this R naught will become 50 ohms if you're scaling this 1 to 50 ohms. So this dash values are the new values. So RS will become equal to the new scaled value of the impedance, and this RL dash will become RL to R naught. So this L, C, and RL are the values for the original design, and the hyphen is the new design. And similarly, now once you have scaled the impedance, we'll also need to scale the frequencies. So we for a low pass filter, we replace omega by omega c in the expression. So the power loss ratio, which was initially PL, become function of omega by omega c, and omega by omega c is equals to 1. Uh, so at this particular frequency, the cutoff occurs. So just replace omega by omega c and multiply inductors by R naught and divide the capacitors by R naught. You will scale the prototype to a proper low pass filter at the desired cutoff frequency and of the correct impedance values. So frequency scaling is done by this expression over here, and yeah, so this is the plot for the power loss ratio for a normalized thing, normalized frequency. And once you have scaled this, this will become something like this. So this one and one thing will scale to the correct cutoff frequencies. And then if you want to do a high pass thing, you just replace this particular frequency by one by yeah, you have to replace this omega by omega c by omega, and this will become high pass. So we'll see this as well. And now the correct values for the new elements after frequency scaling will be omega by omega c Lk. And this particular thing can be written as omega Lk dash, and similarly omega Ck dash, where Ck dash and Lk dash are Lk by omega c, where this Lk is the original the that G and G naught thing that you copied from the table. And when both the impedance and frequency scaling are combined, this will become equal to R naught Lk by omega c, where this Lk and Ck are again that G values that you copied from the table. And for filter, so we whatever discussion that we did was for the low pass prototype, and so from the low pass prototype, all you need to do is frequency scaling and impedance scaling. But if you want to change the low pass to a high pass, what you need to do is um, you divide it with the omega, this particular omega c term over here. You invert, so change the inductor to a capacitor, and its value will be given by 1 by omega c, and and capacitor to inductor changing 1 by omega c into c. And if you want to make this low pass prototype to a band pass, this is how you will change it. So you replace this you use this L value and find out this term over here. So once you have found out these terms, you can replace your inductor by inductor and capacitor in series. And if you have a capacitor, you can replace them by a inductor and capacitor in a parallel, and you can use the C value to find out this term over here. And we have delta over here, which is actually omega 2 minus omega 1. So mathematics behind them is again present in Pozar. I'm skipping this because uh, if you can read this, but eventually this table is all you need to change your low pass prototype to a high pass, band pass, or a band stop. So what I'm trying to say is, once you have done your for example, this is your low pass uh, filter, right? And you want to change it to a high pass filter, you will replace this inductor by a capacitor, and this capacitor by an inductor. And there, for example, you had found their values as LC. Oh, just instead of LC, what you do is you would write them as 1 by omega CL and um, 1 by omega CC. This is your high pass. And if you wanted to change this high low pass to a band pass, then you must know the bandwidth, and then you can change this inductor to inductor plus capacitor, and then this capacitor to uh, inductor and capacitor, something like this. Okay, maybe this became a little scribbled over here. If you come over here, there you have to replace this inductor, right? So you replace this inductor by inductor and series capacitor, and you have to replace this capacitor. And to replace this capacitor, we have a shunt inductor and shunt capacitor. So this will become your this was your low pass. This will become your high pass. This will become your band pass, and the values can be calculated by using whatever L value you had. Then you can find out this as L by omega naught delta, and so on. So you can use this value over here, use this value over here, and use this value over here. So you get the idea, right? So we're just trying to, once you found out your low pass prototype, you can find out high pass, band pass, or band stop. So this is very straightforward if you try to solve some examples. So I'll put them in the assignment. I'll share them in a couple of days with among other assignments. So I've not got time to compile write up complete the assignments and share it. I will do that in a couple of days. So this was the last class. We have completed all the material, and this is all that we intended to cover. We covered the image parameter method, insertion loss method, and the filter transforms. So upon solving the examples, this will become clear. So I'll share and exam. So there are some examples in Podzar. I'll recommend you first solve them. And if you have any questions, you can come back. But I am sure that this won't lead to any questions. They are very straightforward. So that's it. Thank you for attending the course and all the best for your uh, endeavors. Um, I'll share the material and all the recordings together in one email where it will accumulate all the material. And I'll get the certificates for the course processed through the ISSS admin. So that might take some time. I'll recommend everyone to fill up the feedback form as quickly as possible. Maybe in a couple of days, I'll close the form. So the form is essential for you to get your certificates. So that's it. Any questions that you have from today's material or the previous materials or for about this course or anything in general, you can ask them. Else, we'll wrap up this meeting today and this course as well with it.
Yeah, yeah. Anyway, thanks for your valuable time. And since I had actually, I am also doing PhD in high power micro devices like terahertz area. So
Okay.
for making my the basic strong, only that purpose only I attended this course. So here I learned few things from you also. Anyway, thanks. And in future, any doubts or any related to technical thing, sure I will let you. And I need your already you had around 20 classes, right? So I
Yeah.
consolidated PPT, but one or two classes I'm not able to get the PPT because that I'm not able to download from the particular WhatsApp group. So uh, I will check once again. I will let you if something is needed. Otherwise, I can download from ISSS page, right?
So I have not uploaded the PPTs right now to the IEEE website, so I'll do that. But all these PPTs are also available on my website. So maybe I'll share the website link. So over there, I've uploaded the PPT. I think last two classes I have not done. So I'll upload everything on my website and the IEEE website, and also send a zip file on the WhatsApp group as well for all the slides. And for the recordings, I'll compile the links and send them together in the email reminder that I'll send today or tomorrow for the course feedback form and everything. So I'll do that as well. So I'll make sure that all the material has been circulated well enough so that all the participants have them.
Yeah,
So
yeah, sure.
any other thing that you want me to do? So for the
Yeah, yeah.
certificates, it
Any
will
other?
take some time.
Yeah, yeah, no problem. So
Okay.
actually, apart from this course, is there any possibility to carry some part of research in? So actually, I am working in Terax Imaging. So
Okay.
is there any professor in your department or group working in the particular field like Terax Imaging? So is there any opportunity there?
About the opportunities, I don't know. So our lab does not work in terahertz. So Professor T. Srinivas from EC works in the terahertz region and photonics. You can send an email to him or reach out to someone from his group. And there might be faculties in sense department. So Center for
Yeah,
Nanoscience and Technology. So over there, if you find some faculties, you can visit their the department website, and there you can check if there are faculties, and you can reach out to them.
okay, sure, sure. So you told that professor name, right? Can you repeat that professor name again?
Yeah,
Uh,
Professor
you,
T. Srinivas from
oh,
ECE.
okay, okay, okay. Yeah, anyway, I will go.
Yeah.
Anyway,
Okay
thanks for
then.
your. Yeah, yeah.
Yeah. You're welcome. Yeah. Thanks for joining. So I'll just stop the recording now.
Yeah, sure, sure.
Okay, if no